CT datasets can be rendered by multiple techniques in order to best visualize the relationships between anatomical structures. MIP, or maximum intensity projection, is commonly used to visualize arterial and bony structures. In this MIP image, we can see how the kidneys and large blood vessels are sited in relation to the spine and hips. Note that this is not just a single slice of data, but a projection through the dataset. We'll use a schematic to understand this process. In this figure, we have some bony structures represented by the white lines. The bones, however, are over multiple slices and have other occluding structures. So the first slice will contain some of the bone and an occluding structure. We can see the bony structure over a total of 3 slices, with other structures occluding various parts. If we simply overlay the 3 slices, we'll get an image similar to this. While it is close to visualizing the bony structures we want, parts of it are still obscured. In a MIP reconstruction, we project the maximum value across all 3 slices for each pixel of the image. This gives us a result that can much better visualize the bony structures. We can now see an example of this on real data. On the left-hand side, we can see a loop through the 2D slices of a volume. The MIP reconstruction of the slices surrounding the kidney is shown on the right-hand side. Note that in the video we can see only some of the blood vessels in each frame, while in the MIP reconstruction we can see all the blood vessels in a single image. A second method of MIP reconstruction is a rotational MIP. In this figure we can again see the bony structure we are interested in represented by the white line. In this case we are viewing the 3D block of CT data from the top. In this method, a MIP image is first reconstructed in one direction, and then a series of MIP images are created as we rotate the view of the MIP reconstruction. This continues until we have projected around the entire block of data. If we do this on our same example dataset, the first projection would look like this, and the second would be slightly rotated. The result would be a loop of images as such. Note that while your eyes will trick you into believing that the image is rotating in one direction, if you look away briefly or only focus on a specific part, you will note that the direction seems to reverse. This optical illusion is created as the reconstruction is a parallel projection with no added information for depth. We could remove this effect by using a perspective projection or adding depth cues by reducing the intensity of slices further away from the eye. While these two techniques would remove this optical illusion, in radiological practice a parallel projection is used as it retains the exact relationship between objects.